Okay, good afternoon, everybody. If you wrote the makeup quiz, I have them here. I don't have the other quizzes here because I don't want to drag that box of quizzes around with me everywhere I go. I have to do some traveling this week, so I'm away Thursday and Friday, so I can't hold office hours or do the lecture on Thursday tomorrow. So you have a day off tomorrow. Okay, today's lecture is more about pointers and arrays. So there's a set of lecture slides that was just posted to OnQ for today's lecture if you're interested in reading them. Okay, so far with pointers, you've seen that you can create a pointer, have it point to an object. Right? You've seen that you can make a pointer that points into an array, and you can move it through the array using some array arithmetic, right? So you can add 1 to a pointer that moves it to the right. You can subtract 1 from a pointer that moves it to the left. But it turns out you can do a bunch of other things with pointers, right? So I guess in Java and in Python, your references, right, so variables, you can think of those references as just being pointers. And in Java, that's probably actually what they are. So they probably are implemented as pointers underneath the hood. But you know that in Python and Java, you can't do anything with you can't get access to the pointer itself. Right? You've got this reference, and the only thing you can do with the reference is call methods belonging to an object. Right? So that's all you can do with a reference in Java and Python. In C, you can do a lot more with a pointer. Right? So for example, you can take 2 pointers and you can ask, are they equal? Right? So 2 pointers are equal if they both point to the same object. Right? So that kind of makes sense. Right? However, there's other situations where 2 pointers can be equal. So if you have 2 pointers that are both null, meaning they point at nothing, then they're also equal. And the odd one here is the one in the middle. So you can have a pointer, right? So you can have an array. So we'll make it a little array of length 3 here. Right? It doesn't matter what the element type is. You got some array. Right? So you can have a pointer p that points to the first element of the array. Right? It turns out you are allowed in C to safely point to that element there. Right? So that's actually in C, I'll tell you about that in a minute. That's called the too far pointer. So you're allowed to take a pointer to the element that's 1 past the end of an array, and the C language guarantees that that always works. You can't do anything with that pointer safely, but you're allowed to set the pointer so that it points there. Right? If you have 2 pointers that point to that thing there, right, to the 1 past the end of the array, they're also equal, right, which is a bit odd, but it's needed because a lot of old C code actually uses the technique of moving pointers past the end of an array in order to process all the elements in an array. Okay, if your pointer types are different and you try to compare 2 pointers for equality, the compiler issues a warning, right? So if I have a pointer to a double and I have a pointer to an int, and if I ask, are those 2 pointers equal, the compiler generates code for that to work, but it tells you, hey, you're probably doing something odd here, right? Because a pointer to an int is definitely not equal to a pointer to a double. Right? So here's a little example program that compares 2 pointers. Right? So I've got an int object I. Right? I've got a pointer p. Right? P points at I, and I have a pointer pi that also points at I. Right? So p and pi both point to the same object. So you can use equals equals and compare them. Right? So if p equals equals pi is true, then we should get p points to the same object as pi. Right? And if it's false, we should get nothing. So the program, whoa, I got a lot of windows open. So the program is somewhere here. This is, not that. Sorry. Compare pointer. There we go. So it's right there. And if you run the program, so this is compare. Right? It prints out p points to the same object as pi, which makes sense because the 2 pointers point at the same thing. Right? Now compare pointer 2, I think. Is that right? Oh, no, that's not the right one. Okay. Okay, so if you try to compare, in this program here, I've got an object I and I have an object D, right? Their types are different and they are 2 distinct objects. PI points at I, right? PD points at D, right? So are the two pointers equal? The answer is obviously no. They're pointing at different objects, right? So we should get PI points to a different object than PD. Now, when you compile this program, this is one of the instances in C where the compiler actually does try to help you, right? So GCC -O compare, what's this called again? Compare pointer warning. Whoops, and compare pointer warning C. Okay, so when you compile this, you actually do get a compiler warning, right? So when you compile, if you compile a program and you actually see any output from the compiler, something probably went wrong, right? So in this case, you get a warning. The program still compiles and it still runs, right? So it says comparison of distinct pointer types lacks a cast, right? And it tries to indicate where it happened, right? On line 10, right? At that character right there, you're comparing two pointers. They point to different objects of different types. You shouldn't be comparing them because it doesn't make sense, right? However, the program still runs, right? And you get the message that you expect, right? They point to different objects. Oh, sorry, not that one. Control Z. There we go. Okay, so that pointer that's one past the end of the array is called the too far pointer, right? You can have a too far pointer for any array. The language guarantees that that pointer, the language guarantees that you can create such a pointer, right? So I can take P in this case and add 3 to it. 1, 2, 3. Right, so that's P plus 3. Right, the language guarantees that that pointer exists, right? So you can safely create that pointer. Your program won't crash. Nothing bad happens, right? Until you try to dereference that pointer, right? So if you actually try to get the value of the object that pointer actually points at, that's when your program can crash. It can give you back a value that's possibly something that you're expecting. It could give you back any value, right? So undefined behavior, right? Remember in C that means anything can happen, right? Okay, so you need this in you need this because older C code frequently incremented a pointer until it ran off the end of the array. Right, so here's a little example. Here's my array of int. Right? It has 3 elements in it, 1, 2, and 3. Right? The too far pointer you can calculate using the name of the array. Right? So it's just ARR plus 3, right? Or you can take the address of ARR 0 and then add 3. Either way, it's fine. Right? 3 is just the size of the array, right? So start at the front of the array, which is either ARR or the address of ARR 0. Right? Add 3, that gives you the too far pointer. Right? Okay, so P is going to point at the first element of the array. So it's exactly the situation here. Right? Q is also going to point at the first element of that array. Right? And now you can write a little loop. Right? So while P is not equal to the too far pointer, right, you can do something with the pointers P and Q. Right? So for example, I might dereference P to see what the character is there, or to see what the value is there, or something else. Right? To process the next element in the array, you just move P one to the right. Right? So P plus plus. Right? Similarly, if you had a second pointer, right, you could also move that one as well, so Q plus plus. Right? So it turns out there's a lot of algorithms that move 2 pointers through an array. Right? Whether they do it exactly this way or not is another story. Right? But in this example, we're moving them both at the same time. Right? Now, after this loop runs, where are P and Q? Well, P and Q end up one past the end of the array. Right? So I can safely ask, are they the same pointer? So I can safely compare them. Right? What I can't do here is I can't dereference them. Right? If you try to dereference P, so if you try to write star P, right, to get its value, anything can happen. Right? And if you run this example, it's not that surprising. It's going to give you back, this is compare pointer 2. So this one's compare pointer 2, right there. So if you run this program, you end up with P and Q are being equal, right? Because they both end up running off the end of the array. So that's there, right? So P and Q are equal, and it turns out they're both pointing at the too far pointer. Or they're both equal to the too far pointer. Oh, sorry. Control here. All right. A null pointer is a pointer that points at nothing, right? So it points at no object. Right? And you're allowed to assign a pointer so that it points at no object, right? You just use the keyword big N, big U, big L, big L. Right? So all caps null is the constant that's predefined for you as being the null pointer. Right? If you try to dereference a null pointer, undefined behavior. Right? Usually your program crashes. Right? You can also use the integer value 0 to indicate a null pointer. Right? So C says use either null or the integer value 0. What you're not supposed to do is you're not supposed to create an int variable, so int z, and set it to 0, and then use that as the null pointer. Right? So either use the constant 0 or use null, but don't use a variable whose value is 0. Right? So here's compare two null pointers. So P and Q, they both point to no object. Right? Are they equal? This is going to print true, right? Because two null pointers are equal. Now, it's frequently the case that you have to test, is a pointer null or not, right? So it's very common to write a function that takes in a pointer to an object, and for your function to work properly, that function, the pointer must not be null, right? In other words, you really do need an object to do something inside this function, right? So there's there's three different ways to test if a pointer is null in C, right? So you can write if P equals null, which is probably the clearest for people new to C, right? You can write if P equals 0, but this looks like an integer comparison, right? Or it actually looks, or a Boolean comparison. That's the crazy thing in C, right? That could be a Boolean comparison, it could be an integer comparison, it could be a pointer comparison, right? So I would discourage you from writing that. You can also write if not P, right? So this turns out to also work to test if a pointer is null. So here we have all three of them, right? So P is the null pointer. If not P, it prints out P is the null pointer, right? Equals null, and equals 0, right? Notice the avoid doing the following at the bottom, right? So these three are fine, although the last one is confusing, right? What you're not supposed to do is you're not supposed to define your own integer variable, called null in this case, set it to 0, and then compare the pointer to your integer variable, right? You should avoid doing that. If you want to do the P equals 0, then use 0, don't use a variable, right? So this is test for null, right? And not surprisingly, you get 4. P is not a, 4 times P is null. P is a null pointer, right? So they all work to test for null. Okay, now what about this void pointer? Right? So remember, a void pointer is a pointer that's allowed to point at anything, including null. Right? So it can point at any object. Right? You are allowed to test void pointers for equality. So you can ask, do these two pointers point at the same object? Right? So I have a variable I and a variable D, right? So an int and a double. Right? P points to the double in this case. Right? PI points to the integer, and PD also points to the double, right? Now notice that they're types, right? The type of the pointer is void, void pointer, right? So I'm not saying here P is a pointer to double, right? The pointer type is actually void star, right? For the integer pointer, it's void star, not int star. And for the double pointer, it's again void star, not double star, right? So when you do the comparison of PI and PD, right? Now, remember, PI and PD, one points to an int, one points to a double, right? You do not get a compiler warning in this case, right? In the previous example, where you had a pointer to int and a pointer to double, where the types were int star and double star, you get a warning. But now, because the pointer types are the same, you don't get a warning, right? So this compiles cleanly, without warning, and you don't get the message PI points to the same object as PD, because they don't, right? And P and PD, well, they do point to the same object, so you get P points to the same object as PD. So let's compare void pointer. Right, so P points to the same object as PD, but PI does not point to the same object as PD, which is exactly what we expected. All right, so that's equality. Now, if you can compare two pointers for equality, it kind of makes sense that you can also use less than, greater than, less than or equal to, and greater than or equal to compare pointers, right? But this only makes sense if the two pointers that you're comparing are pointers into the same array, right? So the pointers into the same array. So what does less than do for pointers in the same array? Right? So that's P and that's Q, right? In this case here, P is less than Q, right? All you're saying is that P points to an element that comes before the element that Q points to, right? Q is greater than P, right? Q points to an element somewhere later in the array than the element that P points to. Right? So if two pointers point to different elements of the same array, the one pointing at the element with the larger index compares as greater. Right? So instead of using indexes, right, so instead of using an integer index and comparing the indexes, you can just compare the pointers directly. A pointer that points at the too far pointer is always greater than any other pointer into the array, right? So if that's too far, right? So too far is greater than any other pointer into a valid element of the array. Right. Okay, so there's my array 1, 2, 3. Right? P points at the first element of the array. Q points at the second element. R points at the too far pointer, right? So in this example here, P, Q, and this is R, right? So is R greater than Q? The answer is yes, right? So that's going to put R is greater than Q. Is Q greater than P? The answer is yes, right? If you change up the operator to be less than, right? So if R is less than Q, you get nothing, right? If Q is less than P, you get nothing, right? Right, so instead of doing, when you're processing an array, instead of using an integer index, you can always just use a pointer, right? Okay. Variable length arrays. So a variable length array is like a Java array, right? So a Java array, you can create an array using a variable, right? So you make an array of int, and you can make an array of int using a variable to indicate the size of the array. Right? Is that true? Hang on. In Java. No, that's not true in Java. Sorry, never mind. When you use new, you specify the length of the array. So C in C99 decided that, hey, it might be useful to have an array where you can specify where the size of the array is a variable. Now, variable length does not mean that the size of the array changes during the lifetime of the array, right? So an array always has a fixed size, right? What it means, though, is that the capacity of the array is defined by a variable, right? So variable length means that the length of the array is defined by a variable instead of a constant. Let me skip over this slide for a second. I'll come back to this one in a minute. So here I've got a little main function. I'm going to ask the user, in this case, to enter in an array size, right? Less than 20 in this case. Right? So the way that I'm going to get input from the keyboard is with this function called scanf. Right? So scanf is a function that will read the keyboard for input. Right? So the way it works is you specify a variable. In this case, I want to read in a size. Right? So I'm going to the type is going to be size type. That's just an unsigned integer type. Right? So I need a variable in which to store whatever scanf reads in from the keyboard. Right? So I want to read in an int of some kind. So I'm going to create an integer variable here called n. Right? Scanf is going to read the keyboard, right? It's going to look for something that matches that conversion, right? So that conversion, %LU, U means unsigned int, L means long unsigned int, right? Which happens to be the type of size t, right? So that's going to look for some unsigned integer value. It's going to try to store the result in n, right? Now notice that to store the result in n, right, what does the function need? Right? The function actually needs the object n, right? So how do you give it the object n? Well, I can't pass it n. I have to pass it an address to n, right? If this address thing was missing, right, I would be passing it the value of n, right? This is the swap example all over again, right? The value of n is 0. So yeah, the function can set its parameter, whatever it's called, to some other value, but it won't change that n there, right? In order for scanf to change the value that's stored in n, you have to pass a pointer to n. So if you look at the documentation for scanf, that's a pointer to some, that's actually a void pointer, right? A pointer to some object that can store whatever that value gets, whatever that value is, right? Result is 1. Sorry, if result equals 1 and n is less than 20. Result is the number of conversions that scanf is the number of values that scanf was able to successfully convert, right? So there's one conversion here, right? And so at most scanf returns 1, right? It can return 0 if the thing you typed in was not an integer value, right? So scanf returns the number of successfully stored values, right? So if the result is 1, meaning the user actually typed in an integer value, and the value of is less than 20, I'm going to go ahead and make a variable length array. So that's what that thing is right there, right? So ARR square bracket n, right, is an array of n int variables, n int values, sorry, n int values, right? In all of our previous examples, that's always been an integer constant, right? So now I'm telling you it can be a variable, right? So there's your variable length array. The loop just sets the elements of the array from 0 to n minus 1, and then prints the array, right? So now we can go back and look at the print function. Okay, so here's a function called print, right? Print takes in a value n and an array of size n, right? That's what this function is trying to convey, right? So it takes in the size of an array, the number of elements in the array, right? And an array of at least that length, right? And now it prints the contents of the array, right? So if n is 0, right? So if your array is empty, it just prints square bracket, right? Turns out in C, this never happened. No, sorry, I lie, right? So in this case, if n is 0, it just prints out square bracket, right? There are no 0 length arrays in C. So I didn't exactly lie, right? But the way you use this function is you can pass in 0 and everything's fine, right? So no 0 length arrays in C. An array always has length at least equal to 1. If you try to make a 0 length array in C, the compiler will complain, right? Okay, how do you print out the array? So I'm going to print out the first element of the array. So square bracket, then the first element of the array. I'm going to process every other element in the array. So starting at index 1, going up to but not including n, I'm going to print a comma, then the element of the array, and then the element of the array, right? The ip element of the array, right? So that gives me, in this case, 0, 1, 2, 3, right? And then when I get to the end of the array, I put the closing square bracket, right? Notice that there's no handy function or method for you to print an array like there is in Java, right? Arrays toString generates the string representation of an array for you in Java. That doesn't exist in C, right? If you want to print an array, you have to write your own function to do so. This is one way to do so. This function is deceiving, right? So that looks like it takes in an array of n elements, right? That's what it looks like. There's nothing from stopping you from calling this function and passing in an array that has fewer than n elements in it, right? So I can call this with 5 and an array, whose length is 3. And this function will happily go and try to process the 5 elements of the array of size 3. Right? So you get no warning that this might cause a problem. Right? The code will compile, it will run, it may produce something sensible, and it may not produce something sensible, and it might crash. Right? In a later lecture, I'll tell you exactly what C thinks this thing is. Right? But C doesn't think this is actually an array. The second thing in this example is, you might ask, well, why do I have to pass in n? Right? Why can't I just pass in an array? Right? And the answer is because C doesn't actually know how big an array is. Right? So in this when this function receives this array, there's no way for the compiler or for the C runtime to actually know the size of that array. Right? So it is required by the programmer to tell it how big that array is. Right? So that's why that value n is here. Right? Whenever you write a function involving an array, one of your parameters has to be how big is this array. Right? Because there's no way for you to get the size of the array otherwise. Right? A very common mistake is to try to use, size of ARR here. Size of ARR doesn't work. Right? What size of ARR returns here is the size of a pointer. Right? So it always returns 8 on my computer. Right? It doesn't actually tell you the number of elements in the array. Right? I'll explain exactly why that happens in the next lecture. Right? But you have to be very careful when you write functions using arrays. Okay, so does this thing actually work? So VLA1. Here. VLA1. Okay, so enter an array of size less than 20. So I guess we'll try 19. Right? Enter, and there you go. So it actually does work. Right? So we make a variable length array, prints the contents of the array, and then exits in this case. Any questions so far? Yes? If you wanted to get the length of the array, could you divide the size of the array? There's no way to do it inside this function. None. Not even like size of the array? No. The only time you can use size of safely is when you are in the same block as where you declared the array. Right? Either in the same block or in a block that's within that block. So here, like right after I write that line, I can use size of and then divide by size of int, and that'll give you the number of elements. As soon as you pass that array to a function, the function has no idea how big the array is. Crazy but true. That's the way the language works. Okay, size underscore t, I've mentioned this before in a previous lecture. It's just the unsigned integer type of the result of size of. It turns out it's usually unsigned long. Right? Size underscore t can store the maximum size of a theoretically possible object of any type. Right? That's what it's defined as. Scanf is a function that reads data from standard input and tries to convert the data into the format specified by the formatting string. Right? So that, right there. That thing there, that %lu, that's the formatting string in this example. If you wanted to read two things in, you could write %lu, %lu. So that would try to read in two unsigned long values. Right? You could write %lu, %s, and I'll try to read in an unsigned long value followed by a string, and so on and so on and so forth. We'll see more examples of scanf later. Right? If scanf is successful, it stores the data that's read in into the arguments that follow the formatting string. Right? So if you type something in and scanf can safely convert the first thing you type in into an unsigned long, it stores it in n. And size of returns, the number of successfully converted arguments. So in this case, it should always, here it should return 1 if you type in something that can be converted to an unsigned int. Right? It will return some other value, EOF, if input failure occurs before the first receiving argument was assigned. Right? So in this case, if you try to type in something that's not an integer, you end up with this value EOF. Whatever that happens to be, right? You don't actually need to know what EOF what its actual value is, right? It's just a constant. The other thing you're going to see in the course is that C has no standard way of doing error handling, right? This is one of the ways that it does error handling, right? There's a return value on the function. You have to look at the return value to determine whether or not the function succeeded. So here, I have to look at the return value to see if I actually did get a successful conversion from scanf. Because remember, there are no exceptions or things like that in Java, in C. Right? In Java, if you tried to scan something, if you tried to scan something with a scanner, and it can't actually read the value as an unsigned int here, you'd probably get an exception. Right? That doesn't happen in C. Okay, so regular arrays. So the arrays that I've shown you so far, including the variable length arrays, they all have automatic storage. Right? Now remember what automatic storage is? The lifetime of the array is the lifetime of the block in which the array was defined in. Right? So what does that mean? Right? So the lifetime of the array is the lifetime of the block that it was defined in. Right? So if you create a function and you create a regular array or a variable length array inside the function, you cannot return that array back to the caller. Right? Because that array disappears as soon as the function finishes running. Right? So, right, same program, now there's a make array function here. Right? So here we have make array. This makes an array of size n. Right? And you say, haha, you just told me about variable length arrays. So I will make an array of size n. Right? I will then populate that array with the values 0 through n minus 1, and then I will try to return that array. Notice the funny return type here. Right? So the return type for this function is a pointer to int. Right? It's a pointer to int. Right? Why is it a pointer to int? Because I'm returning ARR here. Right? ARR is the name of an array, which in C means the same thing as a pointer to the first element of the array. Right? So what's a pointer to the first element in the array? Well, it's a pointer to int. Right? You cannot return an array from a function. Right? So if you tried to write int square bracket here, the compiler won't allow it. Right? You have to return a pointer instead. Right? So this make array function returns a pointer. Presumably, it's a pointer to the first element in an array. Right? Notice the comment, right? Automatic storage. Right? So what is the lifetime of ARR? Well, it starts on this line here, and then it ends on this line here. Right? So when someone calls make array, right, they get a pointer to something, but whatever was pointed at is gone immediately on this line here. Right? So here we call make array. Right? Local array gets created, pointer to the first element of the array gets returned, and then the array is destroyed right here. Right? So whoever gets this pointer down here gets a pointer to an array that no longer exists. And now anything can happen. I have no idea what happens when you run this. Let's see, array lifetime. So let's see what happens when we run this program. Right? If you're lucky, the program barfs, right? And it does. Right? Now notice I say if you're lucky, the program barfs, right? When the program barfs, it doesn't actually tell you anything useful. Right? So it just has segmentation fault. And you say, well, something went wrong. Right? In Java or Python, it would actually tell you the line number on which something went wrong. Here, you don't get that information. You just get something went wrong. Right? And it's now up to you to go through your program and figure out where did the something go wrong. Right? All right. Okay, so if I can't return a variable length array from a function, right? How do you return an array from a function? Because it sounds like sounds like something you might want to do, right? You might want to call some function that reads in a bunch of file from a file and then returns an array consisting of the stuff from that file, right? Kind of sounds like that function has to make an array and then return a pointer to the first element of the array, right? So there has to be some way to do that, right? And the answer is don't use a variable length array or a local array, right? So the answer is you have to use a dynamically allocated array, right? So data structures like stacks, I guess some of you haven't seen these yet because we haven't gotten there in 124. But a list, for example, right, is a data structure that can grow, right, or shrink depending on how many elements are in the list, right? So you can make a list that has one element in it, then you can add 50 million elements to it, and it now has 50 million and one elements, right? And then you can take out the 50 million elements and be left with one element, right? So the memory for these data structures, right? The memory can't have automatic storage, right? And it should be obvious why it can't have automatic storage, right? Because if it had automatic storage, that storage disappears as soon as the block in which your variable, in which your array is defined in, disappears, right? So if it can't have automatic storage, it needs some other kind of storage. Now you don't want to use static storage, right? Because then it lives for the entire lifetime of the program. So that's no good, right? So that's what the third type of storage is, and that's allocated storage duration, right? And so that's what dynamically allocated memory is, right? So the lifetime of an allocated object begins when the allocation function returns and ends when some deallocation function is called, right? So you're going to call some function to ask for memory, and then you're going to call some function to release the memory when you're done with it, right? Now notice the problem is the programmer is responsible for asking for the memory and then deallocating the memory, right? In Java, you have to ask for the memory by calling new, right? But then you don't care, right? As soon as the Java virtual machine detects that the object is no longer needed, the memory for that object disappears, right? In C, that's not the case. So if you ask for memory but never give it back to the system, you can eventually run out of memory, right? And then your program probably crashes, right? Okay, so there's something called the heap, right? I guess there's something called the memory allocator. Okay, so the dynamically allocated memory is managed by the memory manager, which is not part of the C standard, right? It's part of your operating system. So inside your operating system, there's some software component that is responsible for handing out memory. And then there's another, well, it's probably the same component that's responsible for releasing the memory when the programmer tells them they're done with it, right? The different operating systems have different memory managers. The same operating system can have multiple memory managers, right? So you'll learn about how these memory managers work in your operating systems course, right? If you actually look up for information on C online, you'll often see the term heap and stack, right? So the heap is a chunk of memory that's usually where dynamically allocated objects come from, right? So if you ask for a chunk of memory, that memory comes from something called the heap, right? The heap is just a bunch of memory, right, which the memory manager can control, right? So if you ask for some memory, the memory manager goes to the heap, looks for some memory that's big enough to satisfy the request, right? And then it returns that memory back to the caller, right? Once you get that memory, you're responsible for using it. So you can use it however you want, right? You can put an array there, you can put different objects there, however you want to do, whatever you want to do with it, you can, right? And C gives you the tools to actually put whatever you want into that memory, right? Once you're done with that memory, you have to give it back to the memory manager, right? Otherwise, your program keeps on consuming more and more and more memory until there's no more memory left to be consumed. Okay, so when do you want to use dynamically allocated memory, right? When you don't know how much memory you need ahead of time, right? So if you're writing a program and you can't say how much memory this thing's going to need, right? That's when you probably need to use dynamically allocated memory, right? So for example, if you wanted to implement a list, right, which can grow and shrink as needed, then you're going to need dynamically allocated memory. One of the small disadvantages with dynamically allocated memory is that it's less efficient than statically allocated memory, right? So when you need dynamically allocated memory, you have to ask the operating system for some memory. The operating system has to go out and get the memory, then it has to return it back to you, and then you can use it, right? The other problem is you end up with what are called memory leaks, right? When you forget to return that memory back to the memory manager. Okay, so there's only 3 functions that we're going to use to ask for memory, and there's only one function that we're going to use to return that memory back to the operating system. Right? So those 4 functions are all defined in standard lib.h. Right? So there's malloc, calloc and realloc. Right? Okay, so malloc is the function that you use to allocate uninitialized, so you just get back a chunk of memory, but there could be anything in that memory, right? Uninitialized block of memory of a specified size, right? And in C, all sizes are measured in terms of, in units of car, right? So I'm going to ask for a chunk of memory equal to 1,000 cars, right? Or something like that. Malloc returns a pointer to the allocated memory, right? So you can think of malloc as returning an array, right, of sufficient size, right? So you get a pointer to the first element of that array, right? If for some reason you asked for some memory and malloc could not give you that memory, right, it returns a null pointer, right? Although that would be fairly unusual, especially in this course, right? All right, so here's our make array function. Right? Now remember, though, our previous one using a variable length array doesn't work. Right? So how do you make it work? Right? Well, you use malloc. Right? So in this case, instead of using a, sorry, having a brain fart here. Instead of using a variable length array, I'm going to use a dynamically allocated array and return that. Right? I guess I forgot to fill it in here. But anyway, here we go. So here's malloc. Right? Now malloc, there's only one argument to it. Right? The argument is, how much memory do you need? Right? So this is supposed to make an array of n ints. Right? That's what this function is doing in this example. So I need n ints. Right? Now how big is an int? Well, the size of int is how big an int is. Right? So you ask for that much memory. Right? N times the size of int. Malloc will give you back a pointer to the first element of that array. Right? So if I return that pointer, so I can just return that pointer back to the caller. I think in the actual example, it actually fills in the array. So this is array malloc. Oh, I don't actually fill it in. That was dumb. Sorry. This should really be this. For int I equals 0, I is less than n, I plus plus, and then ARRI. Like that. So I just want to fill it in with some values, right? Remember, malloc doesn't give you back an empty array, right? So in other words, it doesn't give you an array of all zeros. It gives you back an array, or it gives you back a chunk of memory. Anything can be in that chunk of memory. Right? Actually, let's not do this for the time being. So let's not fill in the array, and let's see what we get. So this is dot array. Oops, sorry. Okay, so this is the one where I didn't. Okay, so it doesn't matter. You get back all zeros. Okay, so when I call for this particular program, right, when I don't fill in the values of the array, it looks like I get back all zeros. Right? And you might think that, well, malloc always gives you back an array that's, memory that's initialized to all zeros. It doesn't. Right? The standard specifically says nothing happens to the memory that's given back to you, right? So it's uninitialized. It just so happens that it looks like all zeros, right? You can't rely on the fact that it's all zeros, right? There could be anything here. So if we recompile that program, whoops, array malloc. So this, oh, hang on, Alt-T here. Okay, so now I'm actually going to initialize the memory manually. Right, recompile, and then rerun. Right, so now you get an array whose contents have been safely initialized. Right. Okay, so don't forget, the array that you get back could have anything in it. Right. The problem is on a lot of small programs, it's almost always all zeros. Right. So in this little toy example where we only have an array of size 19, right, you get back all zeros, and now a lot of people new to C will think, oh, I always get back zeros. I never have to initialize the array, right? And then they write a program where you don't get back all zeros and everything blows up and you don't know what happened, right? So don't forget, before you use the array, right, you might have to initialize the contents. Oh, sorry. This is the, okay, here we go. All right, now if you really want a 0 initialized memory, that's what calloc is for. Right? So calloc attempts to initialize a block of memory for n objects, each having the specified size. So its interface is different. I'll show you that in a second. And then initializes all bytes of the allocated memory to 0. Right? So in this case, for integer values, if you have an integer array, you really do get back all zeros if you use calloc. Right? So there's the example using calloc. Now the way you call calloc is different. Right? The first number is how many objects do you want? So I want n in this case. Right? The second argument is how big is each object? Right? So this is size of int. Right? For malloc, it's, oops, here, right? It's just one value equal to the total amount of memory that you need. Right? For calloc, it's two arguments. First argument is how many objects. Second argument, how big is each object. Right? In this example here, it really will print out all zeros. And it's guaranteed to print out all zeros in this case. OK, I think that's good for today. Any questions on today's lecture? Yes? What happens if you don't free? In this case, nothing, because we're only using up we only have an array of size 20, right? But in a big program, in a long-lived program where you're allocating and deallocating, if you forget to deallocate something, it's a memory leak. Yeah. Hey.
Do you have the tests?
If,
I wasn't on the...
Did you write the makeup one?
No. I wrote the original one.
No, I don't. The original one's in my office.
Okay.
You can pick it up now if you want.